That voice never changes. Okay. Welcome everyone. And while Tom is getting our speaker for this evening kitted out, I'll say a little bit about Kit Hardman. My great pleasure to welcome Kit to come and speak to the Society. When it first occurred to me that Kit might be a good speaker for the Society, it was really because I'd seen this lecture on the geology, or some of the geology of Calabria, and I thought, south of Italy, sunshine, what better for a kind of maybe slightly dreary Wednesday evening, potentially weather-wise in Edinburgh. So I'm delighted that Kit is able to come here this evening and present to us on some of the geology of Calabria. I've known Kit for a number of years, kind of on and off at conferences and so on. We've never been in the same place at the same time, but Kit did his undergraduate work at Birmingham and then moved on to do a master's program at Imperial before starting his PhD at Durham under somebody that is a good friend and well known to the Society, Professor Bob Holdsworth, that research was kind of extended into a teaching fellowship, which meant that Kit has spent quite a bit of his time at Durham before moving on to Hull, where he described himself as a scientific officer in charge of one of the main geochemistry lab and LA ICP-MS analytical techniques and so on for Hull. And there was a strong collaboration between Hull and Durham, particularly as the Hull department started its single honours geology program again, which was good to see. However, that has rather hit the buffers a little bit. And that has meant that Kit has moved on and taking a rather new direction, which I'm not sure how much I can actually say about it. He now operates in a role in research collaboration for Her Majesty's government. Need I say more, sort of thing. So at that, we'll allow Kit to come back and say a little bit about his what might begin to feel a little bit like a previous life, talking about the geology and evolution of crystalline basement hosted near surface fissure systems in Calabria in southern Italy. These are really rather intriguing phenomena within geology. So Kit, thank you very much.
Thank you very much. And yes, what can I say? It's fantastic to be back talking about rocks after a short sojourn into the government, and hopefully I will be back as my career continues. But yeah, no, I'm here to talk to you about the rocks of southern Italy in Calabria. Just spacebar here to. Oh, the arrows. There you go, that looks much better. Yeah, so I'm here to talk to you basically today about fissure systems. That was a very long-winded title, using a lot of different words to try and say something ultimately very simple, which is pretty much the theme for this talk today, where we use a lot of words to describe something realistically, which is quite a simple process, and we can really get to grips with where it's at. So when I use the word fissures, and I'm talking about fissures, it's not always clear what I'm talking about, because we have different words for them. The medical field has all sorts of terms for them. But what I'm talking about is the effective near-surface expression of big, deep-seated faults. So I'm not really talking about sort of cracks in soils or anything that's really focused right in sort of the geographer's domain. I really am talking about these geological fault bodies which are expressed in the near surface. And we see loads of modern examples of them. We see the Thingvellir Rift in Iceland, which I think is pictured there in the top left. There's the huge Afar Rift in Ethiopia. There's the whole of East Africa tears itself apart. We have, even today, I was at a talk about the Antarctic shelf and how they're seeing gigantic crevasses and fissure systems, this time on a more human timescale than geologists are used to, but seeing these great crevasses opening up and things fall inside. So we have all these modern examples. We can even have modeled examples, so examples out of Janos Uri's group in Aachen University, where they did sandbox models inside a CT scanner, so they could really get to grips with all those different spaces and voids and cavities inside a fault system. And they found it's very similar processes that we see in modern examples. But what we've been missing was the ancient examples. Where are they in the rock record? Who's described them? Where can I go and have a look at these fissure systems? And we didn't really have such examples. There's a few things referred to as liassic veins, sedimentary dikes, but no one had really described them as this near-surface fissure phenomenon. So that's where we stepped in as our research team. And I should have said at the top slide, it isn't just myself. Of course, no science is a solo effort. There's a huge
Sorry,
collaborative
I
team.
have a problem with the sound. So I think actually the best if you switch that microphone off and you just speak to the laptop.
Yeah, of course.
Try that.
I don't know how to switch it off or anything. I'll just give it to you.
Sorry about that.
That's all right. There we are. Is that any better? Everyone can still hear me. Excellent. Fantastic. Yeah, so obviously science is never a solo effort, and there's a huge research team at Hull and Durham and all over that all supported this research. And so that was our question. We were looking at these three-dimensional voids, looking in the rock record for where we could see examples of fissures. And funnily enough, we did find some. And why did we care? Why on earth is anybody really interested in these fissure systems? And the reality is it's more than just sort of anachronistic science. There's more tangible reasons to do it. If we think about basement rocks as they lifted right up to the surface before we're even forming our sedimentary basins that are later filled with oil fields and all the exciting, fun economic stuff, these sedimentary and these basement systems are exposed to the surface and they're impermeable rocks. But then when we crack them open and we fill them full of sand and we bury them again, all of a sudden we've got these pathways for fluids to migrate. Those fluids can be gold bearing, they could be rare earth element bearing, they could be hydrocarbons. Those voids are then acted on by tectonic forces, which further help migrate and even store them. At the very top of the title slide, you've seen a logo for Hurricane Energy, which is a whole oil and gas company effectively set up to look for oil and gas reserves within fractured basement rocks, exactly the phenomenon that we're describing. So there's a really economic impetus. The other side of the things, the other side that sort of really got me going when I was actively doing research, is this idea that underneath, in this interaction between basement units and cover in sedimentary basins, we often have huge unconformities, huge amounts of missing information from geological time. And we often throw our hands up in the air and say, oh, well, we'll never find out what happened during that time because all the record is missing. But then when we look inside the fissure systems, they're protected, they're shielded, they're held within these impermeable solid basement rocks. And all of a sudden, we've got tons of geological information. We've got sedimentological information from units that don't exist and no longer exist. We've got huge vertebrate fossils found in the southwest coast of dinosaurs that we can now say that lived in certain eras. There are minerals with different textures, preserving fluid chemistries, telling us about paleoenvironments that otherwise we would never have had the information of. So this is a huge wealth of geological information, as well as an economic impetus that has never really been looked at. But why on earth did I need to go and fly from the northeast of England all the way to the south coast of Italy, home of tiny coffees and wonderful beaches and clear water, to study this phenomenon? The reality is it makes an incredible natural lab. Because of the hypersaline waters, we don't have to deal with any sort of lichen or vegetation over the rocks, so the exposures are incredible. The tectonic history is still active today, and we're at the intersection, as you can see there in the right-hand side, of all sorts of different subduction zones. We've got the Tyrrhenian lithosphere and the Ionian lithosphere coming together and coming underneath. There's the whole Pelagian block also coming in, then we've got the Apennine fault belt. There's a whole really active tectonic regime to get to grips with. So that we're all up to speed with the area we're looking at, the Calabrian arc is a bit of a weird one. You can think of it essentially as a series of detached igneous injections into the crust. These are called plutons or massifs, and they form a great arc which spans the subduction zone called the Calabria Peloritani arc. I do apologize for my Italian pronunciation, by the way. It is only going to get worse. And then as this deformation is continued, as all these subduction zones have formed, it effectively floats the lithosphere on top, which gives the boot shape of Italy its toe. So we can thank the toe of Italy to these intrusive igneous bodies and what's happened between them to form these different grabens, and different sort of sedimentary depot centers between. Where we're going to be looking at mostly today is that little yellow box. It's a very small study area. I did go all over Calabria, but the best examples were from there, a place called Copanello, and that's just south of the Catanzaro Fault, just next to the Catanzaro Graben within this massive. So we have a look at a bit more close-up view of that. We can see the pinks, the purples, those are our basement rocks, and our oranges and yellows, those are our cover sequences. And they're mostly Pleistocene, Pliocene, but we're also talking, when we get into grips of the really localized geology, a lot of sort of Miocene sequences as well. The key thing to take away, though, is that between these two units, we have the Messinian erosional unconformity. So this is our major unconformity here that we call between our basement and our cover, and that really forms the top of all these structures. At the very base, we have a foliated, really biotite rich tonalite. So that's a really light rock, but with quite a lot of biotite chucked in there. Some dates from the published literature show that it's about 300 million years old. It's a bit of an interesting story in there because it's got two ages, and the younger age is actually on top of the older age, which is the opposite way round that you'd normally expect from a Pluton because it's being injected from underneath, which means that huge amount of injected magma and then something got injected somehow around the top of it to sit on the top. So there's an interesting tectonic story there, but that's a talk for another day. But within these, the tonalites, what's fantastic about them is that we have such a diversity of structural events. There are pegmatite veins, there are lozenge little shaped mafic enclaves, there are pseudotacholites, these frictional melts and cataclasites, where the rock has just ground itself up, as well as the study that we're going to be talking about and the fissures. So we have a huge structural history to get to grips with and loads of complicated mechanical fabrics that can implicate the formation of our systems. What sits directly on the top of that, you'll be surprised to hear, is effectively just a reworked basement. So this is a basement that was exposed to weathering processes and rolled around on the ocean floor. So we're full of a conglomerate with big boulders of tonalite and a sand that is again made of sort of grains, immature grains of tonalite, some bits of carbonate mud and some calcite cement and that kind of thing. Above that, we have our first sort of sediment system of that basin. It's a Miocene deposit called the San Nicola Formation. That's from a little bit further afield. It's full of fossils. It's just a wonderful marine, transgressive marine sandstone, which directly above that, we have the Messinian carbonates. Now, what's the big stark difference there is that the Miocene formation is chock full of fossils. When this was deposited, those seas were alive with life. When the Messinian carbonates were deposited, zilch, there was nothing. And that's because of the Messinian salinity crisis. Effectively, the oceans got so salty that all life died. And that's the erosion unconformity that we're talking about here, where we have this effectively huge death of life within the ocean. I touched on that structural fabric, and I've got some lovely data to show you. And the key thing is the little simplified schematics that I've got on the left-hand side. Okay, so we start our structural story in Calabria with the basement with simple magmatic deformation. Okay, so we've formed a basic foliation to our rock, and we've got these wonderful mafic enclaves that sort of pick out our foliation there. On top of that, we then have a very slight folding, again, very subtle, but picked out by those mafic enclaves and the development of a few minor ductile shears. This isn't really a major form stage of deformation. The next key thing is pegmatite and aplite veining. So effectively, this is a really late in the story of the Pluton. We've just got some hydrothermal fluids producing just loads of quartz and plagioclase of different grain sizes. But what's fantastic is that because of those mafic enclaves, we can see the offset criteria perfectly. So we can see they've just simply popped open and the cracks. And what you might have noticed with the keen eye amongst you is that the orientation of those is striking almost identically to the foliation, but dipping about 90 degrees. Okay, so as a plan view, if I was looking down, they'd look roughly the same orientation, but when you're looking cross section, you can see in the little schematic there, they're cutting across. The next phase is a really fascinating phase of deformation that I really got stuck into, and I'm happy that I can actually talk about today so I could put a bit more time. But this is a phase of really deep-seated normal faulting, which gave us huge amounts of frictional melts, where the rock rubbed against each other so much it melted and it collapsed itself. We have evidence of a type of alteration, a propylitic alteration, if I get to my, I think it's Latin, where essentially it's a fluid assisted. So we have a huge amount of iron and magnesium rich fluids percolating through this rock at the same time. And we can use that as well as some quartz techniques to tell us that it was about 10 kilometers depth. There's a lot of assumptions in there, but as a ballpark, we're looking at about 10 kilometers deep. So we've tracked our basement so far from its intrusion into the rest of the crust up through a few phases. We've got a little bit shallower, and now we've got our frictional melting and our cataclasite. It's quite characteristically green in the field. The photo doesn't quite give it justice because of some green schist facies, mineral alterations. And then we get to the really sexy stuff. This is the fissuring, the dilatant faulting. And this often reactivates other structures, but it forms its own virgin structures as well. So we have our own virgin orientations that we can extract field data. And what you might have noticed as we're going through is the very early phases of deformation are really well constrained. Okay, so the orientations here are really condensed, nice and precise and accurate. But by the time we get to the end, we have a slightly more sparse groupings. And then when we get to the fissuring, we can see a much sparser grouping. So the orientations we're seeing within the fissures are way sparser than anything that was formed further down. But that makes perfect sense, right? Because when you're really buried underground, the main force you've got to reckon with is your gravity, the weight of the rocks above. When you're up in the surface, you've not got that same kind of confining pressure, and so your fractures can propagate in any sort of which direction they want. The thing that is consistent is the opening direction. Because we have this pre-existing fabric, we can really precisely constrain the exact vectors of dilation that occurred within these bodies. We don't have to use slicken lines because they've not rubbed against each other. They've mostly just popped open, but we can work out exactly what direction they've popped. And what we found was that was almost perfectly north-south. So despite the fact we had a whole array of different orientated bodies, they all opened perfectly north-south. So there's a really big, wider control here on what's causing them to open up. The cataclasis and the sort of the frictional melting, those pseudotacholites that I mentioned earlier, I would be remiss if I were to talk about them and not show you some good photos of them. They really are fantastic. In places, they get up to about 30 to 40 centimeters thick. So these are huge, great frictional melts. The pressures we're talking about here and the energy behind some of these earthquakes would have been earth-shattering. The alterations and things we see in thin section are very characteristic of huge single pulse eruptions with great cooling margins down the outside, where we can see differences between sort of sphaeritic crystal textures and all those cryptocrystalline, weird and wonderful microstructures within them. But we also have brecciated pseudotacholites. So we know this isn't just one eruption, one great big earthquake that just rocked the southern Calabrian coast. This is a series of several earthquakes that have rocked the southern Calabrian coast. If we do our fancy paleostress inversions, when we start to actually reconstruct the tensors and the vectors that occurred, we can actually begin to see that most of our faults are almost perfectly normal offset. So these are faults traditionally associated with an extensional regime where our faults are extending. So how are we generating such significant pressures to generate 20, 30 centimeters wide of frictional melts? And the reality is because they're buried so deeply, and there's such a great confining pressure that when these earthquakes are occurring, when the slip is happening on the faults, a huge amount of energy is being released. So even though this isn't convergent and it is a divergent tectonic regime, we are actually forming incredible pseudotacholite melts. You can see again from the different methods here, I've got a right dihedron in the middle and then a PBT axis underneath. I won't get in too much into the specifics, but they're both consistent with each other, that we're looking at a nice east-west extensional regime. So the picture this is pointing, and this fits with a lot of existing literature, is that at some point during this Pluton's history, there was a really, really rapid exhumation to the surface. Calabria relaxed within its subduction zones, it extended, and a huge amount of material was uplift. And during this uplift, we generated a huge amount of pseudotacholite and cataclasite, which formed a fantastic mechanical fabric. Now that we're good to grips with that, we can finally show you some of the great pictures of fissures. You have to indulge me because I really love those pseudotachylites. The fissures that we're seeing, and I'm going to show you a lot of photos of them, they really can get quite wide. So they can get up to tens of meters wide, and they are invariably filled. And they are filled with sediments, they are filled with fossils, they are filled with mineralization, they are filled with, in the case of that great one on the right there, gigantic boulders that are meters wide. Now, how they were emplaced within these cavities has been a bit of a mystery and has been a bit of debate in the literature and with my collaborators. Some people favor a more injection mechanism when it's buried at depth that these things have actually physically forced in. Others favor a more collapsed structure whereby it's right at the surface and whatever's just floating around on the ocean floor has fallen in. I'll leave it up to the end and we can make up your own minds about that is. Obviously, I'll probably end up steering you in the direction I believe in. What we can think of them, at least for now, is these rather diverse bodies just chock full of stuff. The actual two-dimensional architectures of them, as I've mentioned, they're really quite sparsely orientated with that really consistent north-south opening vector. But when we look at them using our drone imagery, and when we have a look and start to reconstruct those orthorectified, planimetry correct drone images, which is a fancy word for map. So this is effectively just an image map of the top surface of these rocks, and we can extract all our traces of the fault, literally drawing on for hours and hours at a time all the different cracks that you can see. And what we find is that when we look at the different nodes and the branches of how this system is connected, that these fissures are incredibly well connected. So if you start to think of that from an economic perspective, when we start to think of these fissure systems as being connected and fluids being able to flow through them, that's a great news, because that means I can stick a well on the north side and be reasonably certain that stuff on the south will actually be able to flow into that same well. So from an economic perspective, that's fantastic news that these things are connected and connected so incredibly. The other exciting bit of news from a sort of geostatistic point when we look at this is that the distribution there on the graph is effectively power law. And that is you don't normally see from a database this small. Normally you have to collect thousands and thousands and thousands of different relationships within to see these kinds of statistical relationships within fault distributions. What that actually is popping there showing is our aperture. So that's how wide are these bodies. That's not sort of how wide along a trace length, but how wide it is in how far it opened. The kinematic aperture, I think, is the scientific terminology that people like to use. And what we have a mean of is about 40 centimeters. But yeah, they get up to, in the drone images and things, we got up to about 2 and a bit meters. When we look in cross section, some of the larger ones we'll be looking at later, they can get up to about 4 or 5 meters wide. The examples that I've seen in Torbay, the largest I've come across was 40 meters. So this is a fault that is 40 meters wide and filled with stuff. Speaking of the stuff that fills them, they are filled with sandstone, but I would have to take my structural geologist hat off now and put on my sedimentologist's hat and actually start to talk about the structures of them. These are 3D bodies, and as such, they have sedimentary structures. There are bedding that we see quite regularly. We don't see it in every single fissure. That's really important. We see it in, I'd say, about 30 to 40%. That's mostly because water percolation and fluid percolation through these fissures has destroyed any sedimentary structures from deposition. So we don't see it in every single body. We do see where we have it often that there are injection structures almost immediately next to it. So we have this really passive, soft layering of sediment right next to a fault, which has had a really active, really high energy impact of sediment there. So you can understand why we're getting into the debates of, is this a high energy body with sort of low energy eddies, or is this a low energy body with high energy events that only affect certain areas? But my favorite of all the sedimentary structures is something I've seen in every single fissure system I've ever looked at. And it is these pyramidal piles of sediment. And to me, that is the key piece of evidence that I like to use. It's effectively where you have single small piles, sometimes no bigger than my fist, sometimes the size of a small gar, of sediment that has just piled up on top of an asperity. That can be a chunk in the fault wall, or it could be a brecciaclast, it could be anything that's captured and sediment has just piled on top. So that, to me, suggests that that already exists, and sediment is being poured on top and is just piling on top. Okay, and that's preserved in the rock record, which again just shows you the preservation potential we have within these fissures, that we can preserve such delicate structures. The sediments themselves are incredibly porous. They break the rule book in some cases. We have ideas of idealized sediment porosities of, I think, 30-something%. And in some cases, in some thin sections we've got, that does actually exceed that. And that's because the sediments in fissures aren't subjected to the same burial pressures that a standard sedimentary strata would be. Because we've got this lovely bit of basement rock hugging it and surrounding it, it means that all the rock layering on top isn't going to compress it in the same way. So we're not going to destroy that porosity by compacting our grain size, which means that where we have mineralization, it can either completely occlude that space because it can travel throughout that system as much as it wants, or where we only have light mineralization, it just delicately places together the grains. So that's the example on the left-hand side there. All that black space is all cavity. You can see that the grains are already quite sharp, and they are the exact kind of plagioclases, quartz, biotites that you'd suggest from a tonalite. We've even got chunks of pseudotachyllite and that chloritized cataclasites. Oh, it's a tongue twister. And a great diagnostic tool, which is a little bit of carbonate mud. Okay, so this, to me at least, suggested that all of these grains are the exact same material as our biotite-rich tonalite. It's the basement again. It's just been reworked and it's fallen into a cavity. And while it was rolling around and being reworked, it picked up some carbonate mud. And that again tells us that we're looking at a submarine depositional environment. So this basement was exposed to a shallow water. In addition to just the grains themselves, we can get a lot of information from our fossils. We have coralliferous fossils, we have bivalves, we have brachiopods, we have fossils that I can't name because I'm not a paleobiologist. We have pollen fossils, we have all sorts. And so if you remember back to our sedimentary depositional environment, you can think of a bit of an age constraint there. If we have a Messinian strata that's completely afossiliferous, that there is no fossils in there at all, it was way too saline for any life. Yet here we have a load of really fossil-rich horizons. We know that this sediment must be older than those Messinian limestones. So that must have been one of our early basin sequences from above. That must be our source material for this. This photo on, I think, yeah, it's the far right for you guys, is one of my favorites because you have a cataclasite and a pseudotachyllite there. You can see that it's really dark rocks. Those formed about 10 kilometers deep in the subsurface. On the right-hand side, you have that original basement formed right at the base of Earth's crust. And in the middle, you have a load of carbonate mud and a fossil. And the cool part about that is that that rock was taken almost a kilometer away from the unconformity. So that fossil has fallen down for about a kilometer into the Earth's crust until we found it. So that isn't a fossil that's within a sedimentary strata. That's a fossil that's fallen into the Earth's crust so deep, yet is still there, still preserved, still actively, at least as far as I can tell from a 2D thin section, unbroken. I see a lot of broken fossils as well, though, so they're not all perfectly fixed. We do also have injections, so it's not always these wonderful, perfectly preserved, subtle things, often with the really thin silts and mud grains. And we often see these splay networks. I won't get quite into the grips now of how you tell the difference between a slurry injection and a passively deposited sandstone. It can get quite subjective at places. But once you get your eye in, it really is quite recognizable, especially where we have splay networks like this, where it almost looks like someone's taken a cricket bat to a load of sandstone and it's just shocked its way through the rock. When we think about how these bodies form in terms of their wider relationships, we've got to think about two things. One is how deep are they in the surface? How deep do these fissures extend? And the second is how closely are they related to our big, wide Italian coastline forming faults? In this case, it's the Catanzaro fault I formed earlier that completely cuts right the way through Calabria. So if we look at our rocks right at the top near the Catanzaro fault, unfortunately, that is also our shallowest rocks. Right near the unconformity, we see the biggest apertures, but we also see the smallest concentration of injections. So we're seeing the widest fissures but the smallest amount of high energy structures. When we move into sort of a further away, we get about 1 kilometer away from that fault, about 35 meters below the paleosurface. We get much narrower structures. They tend to only be about 13 centimeters wide, but these have the highest concentration of injections. There's lots of clay splay networks and different injection textures within those. And then when we get the furthest point of away, over 2 kilometers away from the fault, and then really far from the paleosurface, that Mycenian erosional unconformity, the top of our basement, this is, I think, 1.1 kilometers away, because it really does go quite far inland at that point. We get a really small concentration of injections again. So it's interesting that the injections tend to concentrate in the middle of these bodies, or at least as within a depth constraint there. But we also see the very narrowest of fissures. And also, when you look at the orientations, the best orientated. My interpretation of that is, as we're getting deeper and deeper into the basement, and we're getting greater and greater confining pressures, that our faults are starting to align into the correct positions for the stress regime. We're starting to have those greater controls and boundary forces that are really starting to force our faults into certain orientations. And they're mostly reactivating some of the older structures. When we think about the depth control of these fissures, the best place was in the middle, it's Copanello Center. And here's a giant map, and you can see a fissure there, which is just knocking on 10 meters wide in places in plan view. And then when we look in cross section, we can see it almost all the way from its surface down to the base of the cliff, which I think is about 40 meters. And that has big cavities within that. That's not just chocked full, every space is filled with sandstone. There are vuggy cavities so big that I can crawl in them. I know because I did. And you can actually stick your head in and look around the different breccia clasts, because it's so unconsolidated. Well, not necessarily unconsolidated, but so uncompacted. It's literally just what looks like fallen in and just stayed there until today. But what we do see, which we see nowhere else, and I've never seen in any fissure anywhere else, is a damage zone. So normally when we think of rocks and faults that are this big, it's going to destroy the surrounding rock around it. When you move something that big, it's going to have knock-on effects. But I've never seen that before, except here, where we have these just very delicate little pop-open structures, which seem to run parallel to the larger fissures. At the very top of that, at a road cutting, we have this wonderful, almost graben structure. And we can see some of those early basin units, the conglomerates that sit right on the basement. They're also normal faulted, and the Mycenian carbonates themselves have growth strata. So this tells us that our normal faulting, our extending, our tectonic activity has been occurring all the way through the basement history, but also through the cover sequences, also through the Mycenian. So this is a really, really tectonically active region, which is evidenced by what we see. If we're related to those wider tectonic features, how does our north-south opening direction that we're seeing with our kinematic data from our fissures, how does that align with the wider tectonic structures? And the answer, thankfully for me, is that it aligns really well. So that great big Catanzaro fault during the late Miocene into Pleistocene had a sinistral transtensional slip. So it was opening up and slipping sort of to the left laterally. And because it was opening up, it's giving a nice north-south extension. So the postulation here is that our fissures are effectively opening up because of motion along that wider fault. Now, this might seem anachronistic and a bit sort of just, right, this is just another nail to add into our story. But the reality here is that if they're caused by big faulting movements, where else can we find them? If it's not just Italy, if it's not just the southwest coast, are they going to be at the bottom of every single sedimentary basin in the world? Because we can't really go down to the bottom of the North Sea and have a look. We can't really go to the bottom of these things. We've got core data, but that often doesn't give us the resolution. So are these fissure systems as ubiquitous as it's looking like from this study, if they're related to these wider tectonic events? Now, it wouldn't be me or anything I produced if I didn't put a load of cartoons in there. So this is just a simple schematic showing you the interpretation that I've come up with for how these formed. As you've probably tell, I much more favor the hypothesis that these things have opened up and things have fallen in. I think that's much better suited to the evidence that we've got. And that all starts with the basement making it all the way to the surface. We actually get a slight bit of weathering, which we do also see. It's a bleaching of the tonalite. We lose a lot of the biotites. And we see that again within some of the clasts. But we have our existing structures. We have those bright white veinings, and we have those green cataclasites and pseudotachylites in that image. We get a marine transgression. So we're now in a shallow marine environment, and we start to break up that basement rock at the surface, and we also start to fault it. So those normal faults have moved, they've reactivated, and we're starting to build fissure systems, and formations are falling in. That microbreccia is occurring, and it's falling in, clasts are falling in, those fossils are falling in. That continues all the way through the Miocene to the top of the San Nicola Formation, where we've got all our fossiliferous material. We keep growing bigger and bigger fissures that keep cutting each other, cross-cutting earlier sequences, cross-cutting the basement. And that keeps occurring as an iterative process right up until the Messinian salinity crisis. We knock the top off the whole thing, and we fill the rest of the system with these afossiliferous hypersaline Messinian carbonates. Now, the key thing to look at here is because of that really chaotic basin floor, we're not capturing every layer of strata in every place. There are some grabens which will contain a breccia, some grabens that won't. The sediment routing, if you think of our source to sink analysis of this, is going to be incredibly complicated. So we're not always going to preserve a perfect sequence. And that cutting off the top is only going to accentuate that further and means it's even harder to work out exactly where our strata came from. Now, as a final piece, because I have time, is that I did go all over Calabria to look at these bodies. That was the best example around Copanello. You can see the amount of data we managed to extract from those rocks. As a natural lab, I don't think I've worked. The only better place I've ever worked fully enough is the Northwest Highlands for its exposures and its ability to get to grips with complicated structural fabrics. But there were examples of these on those starred locations of all places that we visited. The one here is from Palmy, which is an entire cliff, which is just one great big fissure fill. And at the bottom of it is a small town. And some of the buildings in that town have been flattened by boulders that have effectively fallen out of this fissure system. So that gives extra impetus as to why we actually should be studying these, not just from an energy perspective and an economic perspective, but also from a cliff stability perspective. This isn't simple tonalite on this cliff. This is much more complicated fabric. But again, we see those same pyramidal palaeos, same breccia slurries, passive and solid injections, and a characteristic mineralization, which we see called cockade, where you effectively just surround every grain in a very thin layer of cement. But as my voice starts to go, perfect timing, I believe that is it for me. And I thank you very much. As it's mentioned, I am taking a short break from geology, and it was an absolute dream to be able to sign off this early chapter of my professional geological career with talking to your society. So thank you very much for inviting me.